Okay, let's start. So it's been a while since our last lecture. So today we are going to continue with maximum and minimum value. Maximum and minimum values of a function. And since I'm not that good at the iPad note taking and the video recording, so if you have any suggestions, please let me know. I can improve it a lot. Okay, so first, let's give the definition of local maximum and local minimum of a function. So suppose a function f of x and y has a local maximum at AB if fxy less than or equal to fab when the point xy is near AB. And then fab is called local maximum value. Okay, and similarly, if we reverse the inequality, in other words, if fxy is greater than fab when xy is near AB, then f has a local minimum at AB, and correspondingly fab is a local minimum value. Okay, so probably this is too abstract, but I think we already know quite a lot of examples for 1D. So recall in 1D, usually you will have the following questions. For example, so example, what is what are the local maximum and the local minimums for function fx equals sine x? So you may draw graphs for sine x as following. Also, you have something on this side. Okay, if you don't do any restriction for the domain, for example, in that case, if x in R, then you have infinitely many local maximums and local minimums. And if you restrict yourself to some intervals, then you have finitely many. And for example, here we assume the domain is a whole R. Then let's find the local maximum point and the local minimum. So you will have, if you look at the graph, this point, this point, this point will be local maximum. So x equals pi over 2 plus minus 2 k pi. And correspondingly, for local minimum, you will have this point, this point, this point, this point, etc. and will be negative pi over 2 plus minus 2k pi. K just integers, positive integers. Sorry, you start from 0. Okay, if you look at the picture carefully, then actually we already know that for 1D, you will find the geometry associated with the local extremal value, local extremos, is as follows. The tangent line is horizontal. If you don't buy it, we can check. So here the tangent line is this, here the tangent line is this one, and not only hold for maximal, also hold for local minimal. Okay, then this gives us the definition, critical point in 1D. So recall how we define it. We solve this equation. If x satisfies this equation, then we call it a critical point. Okay. Next, we are going to generalize this to higher dimensions. So we first do it in 2D. So suppose we have a function f and consider its graph z equals fxy. And if you consider the coordinates in 3D, you have xy, fxy. Or more generally, you can consider level surfaces. We will discuss it later. Okay, but because some people are more familiar with the gradient, so I would like to write it on this side. This is the equivalent definition of the function from the point of view of a level surface. If we draw a picture, you might have this one, okay, I didn't tell you what the function is, but you can imagine this to be, for example, z equals negative xy negative y squared, negative x squared minus y squared. This helps you to picture the graph, but in the following study we don't really use the exact form of the function. Okay, then you can imagine, according to this picture, which point is local maximal, and you can easily pick out this point. And then you will ask the similar question: what is the corresponding geometry associated with this point? of course, you can derive the similar fact. Tangent plane is horizontal. Okay. Next, we turn back. Use this geometry to determine the numerical criterion for this point, to determine the numeric equations or criterions for A. So think about how to do that. We should use the geometry of the tangent plane. What is the numerical criterion for a plane to be horizontal? That means the normal line. So this normal direction is parallel to z. So here x, y, z coordinates parallel to z. Okay. Now if you use the form fxyz equals z minus fxy, and the last lecture we learned the normal direction is given by the gradient f, and the gradient f is defined by fx, fy, fz. And if you look at the function here, fxy, capital fxyz is z minus fxy. Then you can compute this explicitly. Minus fx minus fy and 1. Okay, then what does this mean? Parallel to z. Parallel to z just means negative fx equal, or just positive fx equals 0, and at the same time fy equals 0. Okay, then conclusion. Solve this equation, you expect the local maximum or local minimum. Okay, but as you can see from this picture, or even from the definition, even though you can solve this equation, get certain points, it's still another job. You need to do another job to determine its maximum, minimum, or neither. So, but those points are quite significant. So this leads us to the following definition, which generalizes the critical point in 1D. So critical point in 2D. So based on this, actually you can make further generalization to 3D or ND. No big difference. A point AB is called a critical point of F if all the partial derivatives vanish. Okay, and the theorem shows that this is a necessary condition for local maximum or minimum when f is good enough. In other words, you only need to search your local maximum and minimum within the critical point. So the theorem can be stated as follows. If f has a local minimum at AB, then AB must be a critical point. We will not prove this. I think if you know how to solve the problem, that's enough. Okay, next let's look at certain examples. For example, if your function is taken to be x squared plus y squared minus 2x minus 6y plus 14, then what is the critical point and if it is local maximum or local minimum. Notice that these two questions are related but not exactly equivalent. So we will show in the solution. So solution for critical point, you need to solve partial x partial y equals 0, and we take partial derivatives. 2x minus 2 equals 0, 2y minus 6 equals 0, and x equals 1, y equals 3. The point is 1, 3 is the critical point. Okay, next we need to consider if this is local maximum or minimum. So we will introduce some convenient method to do this in practically, but here we just do it by brute force. We complete squares of the function fxy. So you combine x squared minus 2x, complete squares, you have this one, and you combine y squared minus 6y, you get this one. Don't forget the constant. Okay, then you have, if you would like to compute, you can do it. Otherwise, you can keep it as is. Okay, then from this, this function must be at least as large as 4. And when x is 1, y equals 3, equals 4. Recall the definition of local minimum. What is a local minimum? Local minimum means all the values nearby the point is larger. Okay, then we call this point a local minimum. So this is a local minimum. Actually, this is the local minimum. And the local minimum value is 4. Okay, actually I should make a remark here. So if a function has a local minimum and local maximum at point a, b, then the function is a constant function locally. Therefore, in the above example, I didn't really check the definition of local maximum because I know it's not constant function. Then if it's local minimum, then you cannot have it as local maximum. Okay, next we look at another example which tells you the category of critical point is strictly larger than the category of local extremal points. So find the extremal, that means local extremal, local maximum, local minimum of f equals y squared minus x squared. According to the theorem, we will look for the local maximum and the minimum within the set of critical points. So first, let's solve the critical points. In general, usually you have several critical points. And x due to negative 2x, y due to 2y. So the solution is xy equals 0. Then 0, 0 is the critical point of the function. Okay, next you need to determine if this point is local maximum or minimum. Since we don't have the criterion here, I will just give you the result. So notice that fx near 0, 0 can take both positive and negative values, no matter how close the point xy is to 0, 0. If you don't buy it, you can test it. For example, when x is 0, y is epsilon, the function is epsilon squared. Here epsilon can be any number greater than 0. Actually, it can be any small numbers. And similarly, if you take y to be 0, you have this. So this is positive, this is negative. And if you consider the center 0, 0, this is 0. Recall the definition of local maximum or local minimum. So what does local maximum mean? fxy should be less than or equal to f0, 0. When xy is near 0. And the local minimum means fxy should be greater than or equal to f00 when the point is near 0. And then you can see here, you cannot get this based on this observation. Okay, then you don't have no local maximum or minimum. So as I said before, the theorem, if you look at the theorem carefully, the theorem only tells you local minimum must be critical point, but never tells you the inverse. The inverse is not true by the previous example. And actually, this example is the stereotype of the critical points, which is not local extremos. So we can draw the picture like the following. So this point, if you look at it, it's saddle point. This point is very important in mathematics. Later on, if you know further advanced classes, for example, partial differential equations, functional analysis, and minimizing, optimization, even computer science, you will need this. When you do optimization, this point is unstable critical point. That means if you perturb it, you can minimize it further. You can slip down here. This is very different from this point. For this point, if you perturb it, finally you will go back to itself. This is called stable. Okay, sorry. Okay, next, if you are satisfied with the previous examples, then we're done with this class. If not, then we would like to ask the following question. Can we have some convenient way to test if a critical point is local maximum or minimum without drawing pictures or without actually computing the values nearby? So the question, the answer is yes. Okay, so first let's recall in 1D, what do you do? Suppose fx satisfy this, then if the second derivative is positive, then you would have a picture like this, so which is local maximum. Similarly, under this condition, if the second derivative at this point is negative, then you have this picture, which gives you local minimum. Okay, then this is the given line along which we will undertake the following discussion. So the 1D example tells you need to look for useful information in second derivatives. I will collect the results as follows without proof. The rigorous proof will be pretty long. Probably you will not get along with. Okay, so suppose f has continuous second order partial derivatives near AB, and suppose that the partials vanishes at this point. Actually, this is same as saying the point AB is critical point. Okay, then here look at 1D case. You need to test positivity of certain second derivative, but here you have a lot of derivatives. Then instead of testing one, we would like to test certain combination, algebraic combination of second derivatives. This is defined to be xx derivative times yy derivative minus xy derivative square. Or if you like the matrix language, you can write it as a determinant of 2x2 matrix. You don't need to know this, but the matrix is called Hessian, and the determinant is called D here. Okay, then our test will based on the positivity of D and some actual properties. So first case, if D is greater than 0 and fx x AB is greater than 0, then FAB is a local minimum. B, if D is greater than 0 and fxx is less than 0, then FAB, oh sorry, this is not so accurate. I should say AB is a local maximum, fxy is the local maximum value, local minimum value. Here same thing. Then AB is a local maximum, and FAB is local maximum value. Okay, C. Oh, don't be confused about this is case A, case B, case C. If D is less than 0, then you don't need to test fxx or fyy anymore. Then AB is not a local maximum or minimum. So actually it's a saddle point. And similar to any criterion, there might be some exceptions. If you are not lucky enough, your determinant is 0, then the test concludes nothing. Next, I will give some explanations for each case. So before that, let me make some remark. So remark 1, I give a star marks here. That means you don't need to know if you don't want. The conditions is the same as saying the eigenvalues of the matrix fxx, the Hessian matrix, has certain signs. For example, case A actually means 2 eigenvalues are positive. Case B, so let's recall case A, you have determined greater than 0, fxx greater than 0. Case B are all negative. I will not continue. If you have interest, you can search online or you can wait for your linear algebra class. Okay, and then remark 2, we will consider some model types. Of the cases in the criteria. So for case A, we take the function x squared plus y squared. Then at 0, 0, your Hessian is given by 2, 0, 0, 2. Yeah, I omit the computation. If you want, you can ask me or just do it by yourself. Not that difficult. And look at the criterion. Criterion means this matrix, if you take a determinant of this matrix, you have 4, which is positive, and fxx is positive, then A applies. Okay, for B, we have this example. So the Hessian matrix at this point okay, sorry, I auto charge. I will stop here and then give another part of the lecture. Sorry about that.